We talked way back in Chapter 11 about how carbocations can be electrophiles to other alkenes. With a small amount of catalyst and a large amount of alkene, the alkenes can add over and over and over again many times. We call these polymers. Depending on the alkene, we can end up with different types of polymers. We can have similar propagation of a reactive species with a radical initiation of a similar polymerization, which is why we talk about polymers here at the end of all things. The first polymer we'll talk about is polystyrene, not because it's so amazing, it's one of the more difficult plastics to recycle, but because it's easy to see the pieces. With polymers, it's useful to be able to identify the monomer, the single unit that reacts with itself to form the polymer. Not every part of the monomer is necessarily linked, but there is always a backbone, also called the polymer chain or the main chain. With styrene, this backbone has an easily recognizable phenyl side chain, which makes it easy to see that the alkene is the source for the backbone itself. The repeating unit of the polymer is related, but not the same as the monomer. The monomer is what exists before the reaction, while in alkene-based polymers, this has always become a single bond in the repeating unit. The number of repeating units refers to the degree of polymerization. We could, for instance, have a longer or shorter version of polystyrene that would have different degrees of polymerization. Polymers produced through radical reactions go through a familiar set of steps. There's always some initiation where an unstable bond is able to readily homolytically cleave to start the reaction chain. Benzoyl peroxide is a fairly common radical initiator. The first radical goes through a radical addition propagation step. The benzoyl radical is incorporated to a chain that has a benzyl radical. The radical can continue to add on for any number of styrenes, until ultimately two radicals meet and terminate. The lower the initial concentration of initiator is, the longer the chain is likely to become before it meets another radical and terminates. There are several categorizations that are useful for describing polymers, the first being based on the type of chain. These are usually separated into carbon chain polymers, or polyolefins, which are typically derived from alkenes, and heterochain polymers, which are often esters or amides interrupting the carbon chains. We can also talk about the functional groups that are in either the backbone, for example polyesters like type 1 or type 7 plastics, or talk about functional groups in side chains like polyacrylate that's in disposable diapers. We often also will classify based on the monomer used to make the polymer, with polyolefins again being an example. Polymers can be homopolymers, like the most common alkene polymers, plastics 2 through 6, or copolymers like plastics 1 or 7, which are esters, or even copolymers of alkenes like ABS, a copolymer of the alkenes acrylonitrile, butadiene, and styrene. It's also useful to talk about how often a polymer branches. For example, polyethylene is both plastic 2 and plastic 4, but the difference is largely in branching. Many of our plastics can be created by radical mechanisms, particularly most of the alkene-based plastics, polyolefins, that we talked about in Chapter 11, which correspond to plastics 2 through 6. The following slides are a super brief overview of plastics 1 through 7. In each of the following cases, see if you can identify the monomer, the repeating unit, and the side chain, the type of chain, the presence of functional groups in the main chain or the side chain, and whether a homopolymer or copolymer, and finally, if branched. Plastic 1 is polyethylene terephthalate, or PETE. Polyethylene terephthalate is a copolymer of ethylene glycol and terephthalic acid, although terephthalate acetate derivatives are often used. Polyethylene terephthalate is often used in single-use plastic bottles. It can't go from food grade to consumer and then back to food grade, so it typically becomes a polyester fabric fiber when recycled, which should give you a hint about how we classify the functional groups in the backbone. Because PETE is an ester, it is sensitive to acid and base degradation and heat. It really isn't meant for long-term use. The first of our alkene-based plastics is number 2, high-density polyethylene. The plastic is made from ethylene, or ethene. High-density polyethylene tends to have very little branching, which gives it higher density. It's used for things like PEX plumbing and for food and product containers. It's also easily recycled. The repeating unit can be written as shown, which reflects the monomer, but is often written as a single CH2 repeating unit as well. Low-density polyethylene, LDPE, is similar to HDPE, but with much more branching. This is much easier to make with radical mechanisms than the unbranched form. It's used in all sorts of stretchy plastics. It's not actually super hard to recycle, but it is hard to mechanically process the plastic bags. Some grocery stores have places to collect the bags for recycling. Polyvinyl chloride, PVC, is based on chloroethene monomers, which have the common name vinyl chloride. PVC has a chlorine side chain every other carbon. Vinyl chloride itself is really toxic, but PVC is used in many water applications, particularly in wastewater. It's also used in flexible plastic toys, like rubber ducks. Pretty geeked about how much those toys end up in my kid's mouth. One of the safest polymers is polypropylene, a polymer of propylene. Because only 2 of the carbons form the backbone, every other backbone carbon has a methyl side chain. This is easy to recycle, but generally maintains whatever colorants were added to the plastic, so new uses tend to be darker, like the broom bristles shown. Many food containers, and particularly food containers intended for multiple uses, are made of polypropylene, like Levi and Iris's straw cups. Type 6 plastic, polystyrene, often gets conflated with styrofoam, which is a brand name for expanded polystyrene. In reality, expanded polystyrene is just one form of polystyrene. There are other forms that look more like other plastics as well. They all tend to be somewhat rigid, which is why they, and that polystyrene man popularized by Tom York, crack. Polystyrene doesn't easily melt due to all of the regular aromatic branches every other carbon, and expanded polystyrene also insulates well. It also makes polystyrene pretty difficult to recycle. The high volume to mass ratio also makes it costly to recycle. It can also be thermally depolymerized to styrene, which can be reused, but that's toxic. Type 7 is technically other, but one of the main forms of other is polycarbonate, often abbreviated PC. Nalgene water bottles are made of polycarbonate. Polycarbonate is a copolymer of carbonate and some diol. Although carbonate itself, or carbonic acid or carbon dioxide, is not typically the source of the carbonate, actually the acyl chloride derivative phosgene is used. If you study history, you might recognize phosgene as one of the first chemical weapons. For a long time, bisphenol A was the diol portion, BPA, used in the copolymer because it can easily be produced from phenol and acetone. Look at the structure shown of BPA and see how it fits into the polycarbonate structure shown. The carbonyl on the right is the part from the carbonate. Everything else is from the BPA. So when people started talking about BPA, which is a known endocrine disruptor at really high concentrations, leaching out of Nalgenes, of course it does. It's one of the main components. But the concentrations tend to be pretty low as long as the plastic isn't heated. The real issue is not the individual exposure from a single Nalgene bottle, but that when this is a major industrial component, it also becomes a major waste. And that's when we're more likely to see problematic concentrations. To solve this, we now use BPS. That leaches out too, but also as an endocrine disruptor. It's less well studied. Another type poly-7 polyester is PLA, polylactic acid. Polylactic acid is a polymer of lactic acid with itself, which works because it has an alcohol and an acid. Lactic acid can be biologically sourced, making it more sustainable. If it degrades or leaches, it leaches low concentrations of lactic acid, which I make every time I run 10 steps. We say that PLA is biodegradable. This doesn't really happen at any reasonable time scale unless in a commercial composting facility. It won't degrade in your compost bin. Moreover, since the plastic can be recycled, it's usually better to recycle compostable cups than to compost them. There's a lot to be said for the sustainability of biological sourcing, but the compostability isn't actually a good use of resources and actually amounts to pretty misleading branding. The examples of copolymers that we've seen so far have been esters with acid and alcohol monomer pieces. Copolymers can also come from two different alkenes or more different alkenes mixed in any ratio to tune the polymer properties. The copolymer shown combines styrene and butadiene to make synthetic rubber. Notice that when the butadiene polymerizes, there are many alkenes that are retained in the backbone. ABS2 is a copolymer of alkenes. The alkenes acrylonitrile, A, butadiene, B, and styrene, S. Again, the three pieces can be mixed in any ratio, and it still is ABS. Polyacrylates are another class of alkene-based polymers, but the alkene is acrylic acid, or propanoic acid, which has a carboxylic acid or carboxylate side chain. Because the polymer has a really polar carboxylate, every other carbon, these polymers tend to be really water-soluble when they're short, and really water-absorbent when they're large. They're used in most disposable diapers. We've already talked about some polyesters, type 1, and each of the forms of type 7 plastics that we've seen. Notice here that the name polyester refers to the main chain, whereas other names referred to monomers, like the PETE and polycarbonate and polylactic acid. Polyamides also occur and are generally more stable than polyesters because they're amides, which are more stable than esters. Common polyamides are copolymers with two of the recognizable forms shown on screen. The top copolymer is nylon and the bottom is Kevlar. Peptides and proteins are polyamides too. Typical peptides are copolymers of amino acids. But here I show the formation of a tripeptide homopolymer of my favorite amino acid, valine. When identifying branching in a chain, usually we are talking about the difference between sets of straight polymer chains, which maximize interactions between the chains, and polymer chains that have multiple paths, which typically interact less strongly. Straight chains can also be linked together, a process called crosslinking that tends to make the polymers far more rigid. A common example of crosslinking is vulcanized rubber. Alkenes left in natural or synthetic rubber can be treated to form disulfide bonds between the chains, which links them in place. This makes the rubber much stronger and much more stable. Natural and synthetic rubber can both be vulcanized. Crosslinking can happen to various extents. Bakelite is a plastic that was really prevalent in the early years of plastics that was almost entirely cross-linked by electrophilic aromatic substitution to the point where there really isn't a discernible main chain, really just links between lots of pieces. Polymers can be named with either IUPAC names based on the simplest repeating unit. In many cases, but not all, this is the same as the trivial name, which is based on the monomer. The trivial name is more widely used when it's different. For example, polyethylene is IUPAC named polymethylene, but almost nobody calls it polymethylene. In most cases, the name would be formed from the name of the monomer with the prefix poly. For example, polyethylene, polyvinyl chloride, etc. Some polymers are better known outside of industry by trademark names like Teflon for polytetrafluoroethylene, PTFE, and plexiglass for polymethyl methacrylate, or PMMA. Polymers based on alkenes can be catalyzed by radicals or acids or even Lewis acids and tend to grow as continuous chains that add one piece at a time. We call this a chain growth polymer. Radicals can terminate between two chains. Many copolymers can grow by step growth. Since they don't have a single growing end, they can react in monomers or in longer pieces. It doesn't really matter. Polyethylene terephthalate is a step growth polymer. Radical polymers tend to be chain growth, but they aren't the only ones. In this example, an epoxide is opened by calcium oxide, which allows it to be the nucleophile with a negative charged oxygen for the next epoxide, and so on. Another interesting polymer class are the urethanes, used in expanding spray foam insulation. Diisocyanates react with alcohol nucleophiles to form a mixed amide ester functional group called a urethane. The components are housed in two separate containers and are mixed together when sprayed with a propellant. As the urethane solidifies, it expands and traps air in propellant, creating an effective insulant. Polyvinyl acetate, PVAC, is another example of a radically developed polymer. Polyvinyl acetate is common wood glue or school glue, Elmer's perhaps. The polyvinyl acetate can be suspended in water, usually with the aid of a polyvinyl alcohol, which is shown in the top right, but when the water evaporates, it leaves behind a solid polymer. Polyvinyl acetate is also required to synthesize the polymer polyvinyl alcohol, again PVA shown in the top right. The ester can be hydrolyzed to yield polyvinyl alcohol. Why couldn't we just use the vinyl alcohol monomer? Try to draw out the vinyl alcohol structure and tell me what you'd think it'd become when it tautomerizes.